Hello students, hope all of you are well. So today we are going to start the topic of the transform and boundary value problem from the unit 1. So in this unit we are going to discuss about the partial differential equation and its different solution technique. So today's lecture is based on the formation of the partial differential equation by eliminating arbitrary constants. Before we are going to start this topic, we need to know some basic thing about the partial differential equation, that is its definition, its characteristic, order and degree, and so on. So let us start our today's discussion. So suppose if we want to discuss the definition of a partial differential equation, then what we can say about it? So a partial differential equation, the short form is PDE, is an equation that involves one or more partial derivatives of an unknown. Suppose say z be the unknown dependent variable that depends on two or more independent variables. So if we are having an equation where we see that dependent variables along with independent variables and their partial derivatives are coming, then such an equation is known as a partial differential equation. For example, the first equation that I have show here, that is a del z del x plus del z del y, that is equals to 0. So this is a partial differential equation because z is treated as the dependent variable which depends on two independent variables x and y, and partial derivatives are present in this equation. Second one, del 2z del x2 plus del 2z del y2, that is another example. Say del z del x equals to a square del 2z del y2, another example. So these are the sort of examples of the partial differential equation. Now we are going to discuss about the order and degree of a partial differential equation. So as we know from our ordinary differential equation point of view, the definition of order and degree are exactly same. So the order of a partial differential equation is the highest order of the partial derivative that present in the equation. So if we have a partial differential equation, we just need to focus on the highest order derivative that present in the equation. That will give the order of the whole partial differential equation. Similarly, the degree of the partial differential equation is a positive integer power of the highest order derivative whenever it not contains any fractional power in the derivatives. Okay, so if we are having an equation where we see that fractional powers are coming, so there we cannot proceed with the degree formation. We have to make the equation free of the fractions or free of the radicals. Thereafter we have to look into the positive integer power of the highest order derivative. So now we are going to discuss about the order and degree of a partial differential equation with some simple example. So here on the left hand side you can see some sort of examples I have written. We need to find out the order and degree of such an equation. So here the first order del z del x and del z del y is present. So order of this equation is first, because more than first order no partial derivative we can see here. And what is the degree? Both first order partial derivatives are having power exactly equal to 1. So degree of this equation is exactly equal to 1. What about the second one? If we see the second equation, here we can see that del 2z del x2, this is the highest order derivative present in this whole equation. So we don't have to look at del z del x term, we have to look at for the del 2z del y2. So here it is the second order, so it gives us the order of the equation as 2. And what is the power of this highest order derivative here? That is also 2. So the degree of this equation is 2. Now we come to this one, del z del y whole to the power 3 by 2 del 2z del x2 plus z. So here we can see this equation is having second order derivative, highest order as the highest order. So order is becoming 2. Now how to find out the degree? As I have told earlier that to find out the degree we have to make this equation free of fraction. So we have to take whole square on both sides so that this 3 by 2 term can be get vanished. So we will left with, that is del z del y whole cube on the left hand side, and the right hand side we have del 2z del x2 plus z whole square, right? So now if we just look at this, on the left hand side we are having highest power 3, but it is coming for the first order derivative. That will not give us the order, but the order is given by del 2z del x2. And what is the power of this one? The power of this one is 2. Therefore the second order and the degree is also equal to 2. Now come to the fourth example. So here we are having del z del x on left hand side. On the right hand side, inside the sine function, del z del y is coming. So remember, if that partial derivatives are coming inside any kind of function, it can be logarithmic, it can be trigonometric, it can be exponential. For such case, what we have to think? We have to think the expansion of the function. Okay, so now here the order of the partial derivative is 1, because throughout the expression order is not going to change, it is first order only. But how to find out the degree? If we just write down the sine z expansion on the right hand side, so we have z plus del z del y minus z plus del z del y whole cube by 3 factorial and so on, because this expression can come from the Taylor series expansion. So right hand side we can see the power of del z del y gradually raises, right? So this power will go up to infinity, but infinity cannot be treated as a positive integer because it don't have any fixed value. For such a case we have to write down the degree either as not defined or the degree as 0. Okay, so this is the case whenever we are having any kind of partial derivatives within the function. Now we come to today's topic, from where we can have the long type of question, that is the formation of the partial differential equation by eliminating arbitrary constants. So here let us think about one expression that is given to us, that is f of x y z a b equals to 0. Now remember, for this whole chapter we treat x and y as independent variables and z as the dependent variable, because z is a function of x and y that we have written here. Now here the arbitrary constants are a and b, and that one we have to eliminate. So how to eliminate this? Let us have a look. So here if we just think, so we can see that f is basically depends on x, y as well as z, but z is depending on again x as well as y. So if I want to differentiate the expression 1 with respect to x, how we can do this? Because from f to x one direct derivation we can do, so we can write it as del f del x. That can be done directly, plus f to this x, because this x we cannot go directly, we have to stop here in this z point. So here we have to come from f to z, then z to x, right? So we have to apply the concept of the chain rule. So f to z, that is del f del z, and thereafter z to x, that is into del z del x, and right hand side is 0, so this is going to be 0 also. Similarly, if we want to differentiate one partially with respect to y, same scenario is going to happen. One function f is directly depend on y here, so we can write down it as del f del y, but it is not completed. We are having some more terms, because f depends on z, z depends on y, so we can write it as del f del z into del z del y. This is equals to 0. So basically what we have to do, we have to eliminate this a and b from equation 1, equation 2 and equation 3 if it is needed only first order derivative, but if we need higher order derivative then we have to proceed further. Now how to eliminate this? That elimination process is completely depends on you. There is no hard and fast rule how to eliminate this AB. Whatever method you want to apply, you can apply, and you have to delete A and B to get one equation or get a relation, that is phi of x, y, z, del z, del x, del z, del y equals to 0. So this will be your desired partial differential equation. Now some useful notation that throughout this chapter and this unit we are going to use, that is the partial derivatives and their symbolic form. So remember this, del z, del x will be symbolized by p, del z, del y will be symbolized by q, del 2z del x2 double derivative or second order derivative with respect to x is symbolized by r, del 2z del x del y will be symbolized by s, and del 2z del y2 it will be symbolized by t. Now the working rule that we need to follow before we are going to start the problems, that is the relation between the independent variables and the arbitrary constants. Suppose we are having a function which contains some arbitrary function and we have to eliminate it to form the partial differential equation. So this note basically deals with that. Remember, if the number of arbitrary constant and the number of independent variables are in equal quantity, then what will happen? Then the partial differential equation will be of a first order and it will be unique. That is, if we are having is x and y as the independent variables and a and b as arbitrary constant, number of arbitrary constant equal to number of independent variable, then the partial differential equation will be first order and it will be unique. Now the second scenario is that if the number of arbitrary constant is less than the number of independent variables, that is you are having more independent variables than the number of arbitrary constant, then you have partial differential equation, but that will not be a unique partial differential equation. It is not a unique partial differential equation. You can have more than one answer and all answers can be correct. Third case, if the number of arbitrary constant is much more than the number of independent variables, that is you are having 3 or 4 arbitrary constant but the number of independent variable is only 2, then we have partial differential equation but not first order, it must be higher order partial differential equation. So in this topic we are going to explore all these 3 cases one by one. So let us start with the problems. So now the first question that I have given here, that is eliminate a and b to form a partial differential equation from the expression z equals to x square plus a square multiplied with y square plus b square. So how to do this process? Suppose this expression we treat it as equation number 1. Now we have to differentiate equation 1 partially with respect to x one time. So if I differentiate del z del x, that is going to be 2x this term, and y square plus b square will be treated as constant because that term does not contain any x. We are doing partial derivative here. Similarly, if we differentiate this equation 1 partially with respect to y, we get 2y, it is going to be x square plus a square. Now if we just apply the symbolic notation that just we have learned, p stands for del z del x, q stands for del z del y, so we have from here p equals to 2x y square plus b square, and similarly q equals to 2y x square plus a square. Now how to eliminate this a and b? From this two, obviously all of you can be able to understand that y square plus b square, this value I can write it as p upon 2x. Similarly, from the second expression, x square plus a square can be written as q upon 2y. So you get two values which are having the main problem with us, y square plus b square, x square plus a square. This a and b we have to eliminate, right? So we get this two value, and we know from equation 1 that z equal to product of these two terms. Therefore we can write it as z equals to q upon 2y multiplied with p upon 2x. So just cross multiplying, we have pq on one side, another side we have 4xyz. Okay, so this is the desired partial differential equation. Now here you can notice that in this equation 1 we are having only two arbitrary constant a and b, and how many independent variables are there? Only two, x and y. That is why we are having first order partial differential equation, because the first order derivative we have done here, and this partial differential equation is unique, so it comes under the first case or first category. Now we come to the second type of problem. Suppose we want to eliminate one arbitrary constant from a given relation. Say eliminate a to form a PDE from the relation z equal to a plus x cube into y. So here what we can see, we are having only one arbitrary constant but two independent variables, x as well as y. So now let us differentiate equation 1 with respect to x one time. So we have 3x square y, right? X cube derivative is 3x square and this y will be as it is. Now differentiate with respect to y, what we have, del z del y equals to y derivative will be 1, so a plus x cube. What is the value of del z del y in symbol? That is q, so q equals to a plus x cube, right? Now if we just look at the first equation, then on the left hand side we have p, and that is equals to 3x square y. So it itself gives a partial differential equation of first order. Similarly, from second one, q equal to a plus x cube. If I put the value of a plus x cube in the expression, then we have z equal to qy. That is another partial differential equation. So here we are having two partial differential equations. Both are of first order. Why we are having more than one partial differential equation? Because the number of independent variable is here exactly 1, but number of arbitrary constant is exactly 1, but number of independent variable exactly 2. Now we come to some more cases. Suppose eliminate a and b to form the partial differential equation log of az minus 1 equals to x plus ay plus b. Process is same. First of all, we have to differentiate the expression with respect to x. So now what is the derivative of log x? If we just try to remember, the derivative of log of x is 1 upon x, right? But what is the derivative of log of ax? Then this will be 1 upon ax into a, because we have to first take the derivative of log of ax, then we have to take the derivative of ax, right? So it will come like this. So here log of az minus 1, if we take the derivative, what we will have, that is 1 upon az minus 1 multiplied with, if we just go inside it, we are having az minus 1. So az minus 1, if we differentiate partially with respect to x, what we have, a into del z del x. That is equals to right hand side derivative of x exactly equal to 1. So on the left hand side we have a by az minus 1, del z del x is our p, that is equals to 1. Similarly, let us differentiate partially with respect to y. We have 1 by az minus 1 into, look at inside, az minus 1 derivative is a into del z del y. On the right hand side, if we differentiate with respect to y, we have this term only, a into y, so we have a here. So q by that is a by az minus 1, because this a are going to be cancelled here, so del z del y is your q, so q by az minus 1 equal to 1, so value of q is coming as az minus 1. So from 1 and 2, what we can write down, a upon az minus 1 into p equal to 1, and q value is az minus 1, so a upon q into p, that is equal to 1. So a value already you got. What is the value of a? A equal to q by p. Now put this value of a in this expression 2, or you can put this value of a in expression 1 also. Same result you are going to get. Now after substituting a equal to q by p in equation 2, we have q equal to q by p into z minus 1. After simplification, we are having pq equal to qz minus p. So this is our desired differential equation. Now let us come to the fourth problem, that is eliminate a, b and c to form a PDE from this expression x square by a square plus y square by b square plus z square by c square equals to 1. Okay, so now if you look at this equation, we are having three arbitrary constant a, b and c, but number of independent variables are here x and y, only 2. So we are having the third case, that is number of arbitrary constant is much more the independent variables. So let us differentiate expression 1 with respect to x. We have 2x upon a square, first term, y square by b square, partial derivative with respect to x is going to be 0. Say third one, z square derivative is 2z by c square, derivative of z with respect to x is del z del x equals to 0. So in terms of p, and this 2 will get cancelled out, we can write down x upon a square plus z by c square into p equal to 0. This is equation 1. Similarly, let us differentiate with respect to y. We have y upon b square, z by c square, q equal to 0. That is expression 2. Now just see equation 1 and equation 2. After taking the first order partial derivative, only one arbitrary constant is getting eliminated from the given expression. In the given expression, we are having a, b, c, 3 arbitrary constant. But after doing the first partial derivative in equation 1 or in equation 2, we are still having 2 constants, right? So we have to proceed further. That means we have to go for higher order derivative. Now the question is that to which equation we have to derive with respect to x or with respect to y. Now suppose we want to derive the equation 1 again with respect to x, then what will happen? X upon a square, this will become 1 upon a square plus now 1 by c square, and derivative with respect to x will come for the term z into p, that is equals to 0. So after doing this, still we can see a and c both will present there. We will not be able to eliminate if we differentiate equation 1 again with respect to x. Similarly, if we differentiate 2 again with respect to y, still 1 by b square will be there. We have to go for higher order derivative, but not with respect to x for equation 1, not with respect to y for equation 2. Then with respect to what? We have to think here. See, we are having x upon a square term. If we differentiate equation 1 with respect to y, then this term will completely get vanished, right? Or if we differentiate equation 2 with respect to x, this term will get completely vanish, right? So we have to decide this moment that we have to derive equation 1 partially with respect to y or equation 2 partially with respect to x. So anything we can do. So suppose we are differentiating equation 1 partially with respect to y. So let me do the derivation here. So if we want to do del y of z upon c square, p I am writing as del z del x, right? So what we have seen, 1 by c square will come outside, del y of z into del z del x, that will exist. Now if we have to differentiate this, we have to apply the uv rule of the derivative. U constant, derivative of v, plus v constant, differentiation of u. So here we can write down 1 by c square. First we have to differentiate z, so del z del y, keeping del z del x constant, that is del z del x, plus now keeping z constant, differentiate del z del x with respect to y, so it will become del 2z del y del x. So now in symbolic form what we have, 1 by c square, del z del x is our p, del z del y is our q, plus z into del 2z del x del y, that is equals to s. So we have 1 by c square pq plus zs. So we have this term, right hand side is 0, so it will be 0. So we can multiply c square on both sides, so no such arbitrary constant will remain here. So our final answer is pq plus zs equals to 0. So with this example, today's lecture I am going to end or close now. Please follow the other videos for more detailed analysis of the partial differential equation. Thank you all.